Today I'm going to talk about some of our recent work on all-scattering path integral formulation of light transport. So I want to be able to render scenes with volumetric media, and the volumetric media found in these images is typically less difficult to render because the media has a constant density. Previous work has developed an arsenal of techniques for handling media like this, but we'd like to be able to handle more complex media that's more colorful and has more interesting appearance. Today, we're going to make it easier to handle this complex volumetric media by enabling path tracing techniques to be combined in spatially and spectrally varying media. More and more often, path tracing is being used as a tool to render these types of scenes. So path tracing handles these scenes by simulating light traveling through volumetric media. The value of any pixel is calculated as an integral over all possible light paths that pass through the pixel. And while we can mathematically represent the path integral this way, we have to calculate the integral with a Monte Carlo estimator that samples paths of light and evaluates their contribution. We can sample paths using a variety of strategies, and each strategy is going to have a different PDF. So a commonly used strategy is to sample directions and distances, and so on and so forth until the path happens to collide with the light source. We could also decide on the last segment of the path to just connect directly to the light source. And we can even create more elaborate sampling strategies. In this example, we construct a path of length 1 from the eye and a path of length 2 from the light, and then we force a connection between them. More generally, though, we want to design a strategy with a PDF that's proportional to the path contribution function in order to minimize variance. The path contribution function is the product of several local operators, and perhaps the two most important are the phase function, which measures how much light scatters in a given direction, and transmittance, which measures how much light is attenuated along path segments. So since the path contribution function is made up of local operators, we can importance sample these local operators. Most phase functions and their corresponding PDFs are analytically computable, and this makes importance sampling directions straightforward. Transmittance and its corresponding PDFs can be computed analytically only if the medium is simple, for example, if its density is constant. If the medium is heterogeneous, that is, the density is spatially varying, the PDF can no longer be computed analytically, which means that the entire path PDF can't be computed either. However, we can note that since the PDF is proportional to transmittance, it will cancel out with transmittance, so that we don't need to know how to calculate it anymore. This is a nice trick in a single strategy estimator, but we don't want to use just a single strategy estimator. In general, there's no best sampling strategy. Each strategy may perform best in a specific scene, or even within a particular region of a given scene, and so we'd like to be able to combine several strategies. In surface rendering, this is predominantly handled through multiple importance sampling, an importance sampling framework that can intelligently combine multiple estimators. Yet volumetric MIS is limited by what techniques it can combine, since the cancellation trick only works when free flight sampling strategies are identical across path sampling strategies. In order to reap the full benefits of MIS, we need to be able to calculate the PDF of sampled paths. For the past 20 plus years, MIS has been a major contributing factor to the adoption of path tracing for surface rendering in production settings, and our goal in this talk is to find a way to bring this powerful tool to unbiased volumetric rendering without any major limitations. So we accomplish this through the introduction of an unbiased analytic path PDF in spatially varying media. And we use this path PDF to enable MIS in spatially and spectrally varying media. And this lets us generalize and improve several existing techniques. Today, volumetric path tracing techniques fall into one of three classes that can be characterized by the media they handle, whether they're unbiased, and whether the path PDF is known. Analytic solutions meet most of our criteria, yet they're only feasible within media with a simple density. Regular track and ray marching offer solutions that can approximate any media and compute a PDF, but the fact that they only approximate a medium makes them biased. And finally, the most popular set of techniques for volumetric rendering today are null collision algorithms, which employ the clever use of rejection sampling to generate unbiased samples in heterogeneous media. And prior work has really shown that these techniques will give the right sampling distribution, but that we can't evaluate the PDF as a result of the rejection sampling process. So let's take a look at the rejection sampling process more closely and see why it prevents us from knowing the PDF. So we can't sample the free flight distance or evaluate the PDF of sampled distances in heterogeneous media. Null collision algorithms partly work around these limitations by homogenizing the medium with fictitious particles that don't affect light transport. That is, they simply scatter light forward. The homogenized medium has a constant density, and so we know how to sample distances. So let's see how delta tracking leverages this insight to sample unbiased paths. We begin by sampling a direction in the medium. And next, we sample a distance with respect to the homogenized medium. And we check to see whether we've hit a real or fictitious particle. If the particle is fictitious, we continue forward and we sample another direction. And we continue this process until we reach a real collision. Now that we've reached a real collision, we can get rid of the intermediate steps, and this process gives us a distance that we sampled in the heterogeneous medium, and it's just the sum of the distances in the homogenized media. Yet we don't know what the PDF is since we generated the distance samples using this rejection sampling process. Again, we sample a direction, and then we perform a rejection sampling process in order to sample another distance. So once again, we've sampled an unbiased distance, but we don't know how to evaluate the PDF of a distance sample in heterogeneous media. So this is really the crux of the issue. We know how to sample unbiased distances, but this doesn't help us evaluate the PDF in heterogeneous media. And this is really frustrating because we have a perfectly good path, and as a result of not knowing the PDF, we can't combine it with other sampling strategies. So what can we do to overcome this? In our formulation, we realized that you don't need to be able to calculate the path PDF in heterogeneous media. If we look back at all the sampling decisions we made, we see a different path, and we can make sense of this path if we view it in the homogenized medium. And in the homogenized medium, we'll evaluate the probability of each distance sample. And finally, since the medium is homogeneous, we can evaluate distance samples analytically, and so we know the path PDF. Since we can evaluate the path PDF in the homogenized medium, we simply perform our entire rendering procedure in a path integral space defined on media homogenized with fictitious particles. Although we end up interpreting the PDF differently, the sampling procedure is exactly the same as the sampling procedure we perform in heterogeneous media. The fact that the fictitious particles don't affect light transport means that integrating over our path integral space will provide the same results as integrating over a classical path integral space. So our path integral in the homogenized medium, which we refer to as the null scattering path integral, has three main differences from the usual volumetric path integral. First, the path integral contains both real and null scattering vertices. Since we represent volumetric media stochastically, this means that we have to sample the scattering type. Secondly, in null collisions, we always have to sample a specific forward direction. As a result, null collisions can only exist on a straight line between any two real scattering events. And this is similar to when we deal with specular surfaces, and it actually forms a specular manifold. Finally, since we're dealing with a homogenized medium, the transmittance between any two scattering vertices, no matter what type of scattering, is calculated with respect to the real and the null density. And since we can always choose to make this density constant, the transmittance is computed analytically. So you can see our paper for more details on the path integral and its formal derivation. As we stated earlier, previous work has been limited since estimators were either limited to simple media, biased, or use sampling methods where the PDF was unknown. Now we have an unbiased PDF that is analytic in spatially and spectrally varying media. And with an analytic PDF, we can finally combine sampling strategies with MIS in spatially and spectrally varying media. And this lets us build robust estimators that can handle the sort of complex volumetric media that we may want to use in a production setting. We demonstrate this in several experiments in our paper. For the purpose of this talk, we'll focus on two sets of results. Here, we have two sampling strategies, unidirectional and ratio next event estimation, and we'd like to be able to combine them into a single estimator using multiple importance sampling. In the classical path integral space, unidirectional sampling and ratio next event estimation both have an unknown path PDF. The unidirectional strategy samples distances proportional to transmittance. This is called delta tracking. And next event estimation doesn't really sample a distance on this last segment, it just makes a connection directly, and this is called ratio tracking. Since the free flight distance PDFs vary, we can't use a cancellation trick and we can't MIS these approaches. Previous work has usually worked around this problem by replacing ratio next event estimation with delta next event estimation so that both methods have the same distance sampling strategies. This effectively performs MIS only on the directional sampling, and we lose the ability to use ratio tracking. In our path integral, we reinterpret these sampling strategies in a homogenized medium, so the PDFs are both analytically computable now. Note that the distance samples are now proportional to the homogenized medium, so they can be computed analytically. The directional samples are the same as they were previously and also are analytic. Also, I want to note that we've purposely kept out the probability of sampling vertex types for simplicity's sake. But to give you a sense of how this operates, notice that unidirectional will always sample vertex types that are proportional to the ratio of real to null density. Ratio next event, on the other hand, does the same as unidirectional except along the segment that connects the last real scattering event to the light. Along this segment, we force all vertices to be null, which is analogous to forcing the path to reach the light inside of the classical integral space. So the main takeaway is that in our path integral space, we can evaluate the PDF for these sampling strategies, which means we can combine them in MIS, both the directional and the distance sampling components. So now let's look at some results. In all of our results, we measure medium lookups times unit variance, which is a render-agnostic measure of variance. And given that medium lookups are usually the bottleneck in volumetric rendering, this gives us a good measure of how well a technique is performing. So let's consider how well these estimators work in a test scene. We have a highly forward scattering medium that's being illuminated under two different conditions. On the left, we have a small light that's completely misaligned with the phase function, and on the right, we have a large area light that is partially aligned with the phase function. Unidirectional works well when the light source is aligned with the phase function, but it fails otherwise since it'll rarely sample a path that hits the light source, and if it does, the path may be terminated before it even reaches the light. Next event estimation complements unidirectional really well. So it introduces a lot of noise when the phase function is peaky and aligned with the light source, because it's going to choose suboptimal samples that fall outside of the phase function. But unlike unidirectional, it handles the complete misalignment well. It will sample directions towards the light and be able to force a connection using ratio tracking. So this test exemplifies a sort of scenario where we need to combine sampling strategies in order to build a robust estimator. As expected, unidirectional performs poorly with the left scene, and ratio next event estimation performs poorly on the right scene. So if we flip back and forth, we can see that we really need to combine these strategies in order to have an estimator that can handle both the left and the right scene. So here we combine methods using directional MIS, which combines directional samples for the phase function and the light source. It does a fairly good job with both scenes, but the left scene isn't able to use ratio tracking, and so it's somewhat noisy. When we properly MIS the two strategies, our approach is able to use ratio tracking, and ratio tracking drastically reduces the noise in this scene, where we rely on next event estimation to reach a small light source. We do, however, perform slightly worse in the right scene, since ratio tracking is incurring lookups without contributing much to variance reduction. And flipping between directional MIS and our method, we can see that our approach provides a more robust estimator overall. So another common scenario where the distance PDFs vary across sampling strategies is spectrally varying media. In spectrally varying media, each wavelength of light interacts differently within the medium, and this gives us one strategy per each wavelength of light. Usually the differences in these PDFs are based on the differences in the density per wavelength. Therefore, when we homogenize the medium per each wavelength, we end up with wavelength-specific majorants. The majorant is the density of the homogenized medium that we use for distance sampling. We call a majorant tight if it's the smallest majorant that would homogenize a medium. We usually want tighter majorants since the higher the majorant, the shorter the sample distance is, and therefore the more expensive the sampling routine. The simplest way to handle these scenes is to render each channel independently using a tight majorant. Although independent tracking avoids conservative majorants, it has to render each wavelength separately, and this introduces color noise. Previous work has found clever workarounds, though, to avoid these limitations. Spectral tracking, for instance, homogenizes all wavelengths to the same majorant and finds a way to guarantee bounded variance. Spectral tracking can be expensive, though, if one wavelength forces it to use an overly conservative majorant. Additionally, spectral tracking has the same inability to properly MIS ratio next event estimation that we discussed earlier with the bunny scene. Since we can calculate the path PDF, we're able to combine spectrally varying sample strategies using MIS. So this gives us the benefits of both independent tracking and spectral tracking. And additionally, since we can now perform MIS, this means we can augment the 3 wavelength-specific strategies with ratio next event estimation. So to see how these techniques perform against each other, we'll look at the 2 smoke plumes here, each with a different set of spectrally varying densities. So let's start with this bluish plume, which has a single channel with a much higher density than the other 2. Independent tracking in this plume is cheap, since we use tight majorants for each channel. So we can take a large number of samples even though we have to path trace each channel separately. Still, there's a lot of color noise because of the fact that we're handling each channel separately. Spectral tracking is extremely expensive on the other hand, so while it has much less color noise, it isn't able to take as many samples. As a result, it has slightly higher variance than independent tracking. Finally, spectral MIS, our approach, can take about as many samples as independent tracking, but can use those samples across all wavelengths. As a result, spectral MIS has the lowest variance. Not all spectral scenes, though, will have a single channel with a much higher majorant. In this smoke plume, we're going to compare majorants that are much closer. And in these cases, independent tracking isn't going to be able to take drastically more samples than the other methods. And it still has the issue with color noise from before. So as you can see here, this method isn't particularly effective for this smoke plume. Spectral tracking will actually perform better than independent tracking now. It doesn't use an overly conservative majorant, and it avoids color noise. Spectral MIS still avoids most color noise, but the tighter majorants don't have as much of an impact here. Instead, the noise that's introduced by undersampling the green channel's majorant is not offset by the cost savings of using a tight majorant. As a result, we perform just slightly worse in spectral tracking. But unlike spectral tracking, which is limited to directional MIS, spectral MIS can also be combined with ratio next event estimation, which allows us to outperform spectral tracking. This is the main perk of using MIS. We can combine several arbitrary strategies to build extremely robust estimators. To summarize, we've introduced a new path integral that operates in homogenized media. We saw that this path integral has an unbiased and analytic path PDF, since transmittance is analytic. And finally, these path PDFs can be used to perform MIS in spatially and spectrally varying media. We think there are a lot of interesting directions for future work, including a unified null scattering framework that includes both surfaces and volumes with null scattering. We think a similar null scattering path could be found in potentially correlated media or media with non-exponential transmittance. I think other light transport algorithms could potentially make use of our framework. And finally, we think that other rendering techniques such as photon planes or volumes may be able to use our path integral to extend to heterogeneous media.